Hello, I'm Daryl Booth. I'm Excella's General Manager for Environmental Health. This is a presentation to the National Environmental Health Association for their 2021 Annual Education Conference. My journey with machine learning and artificial intelligence started about a year and a half ago. You see, we use Microsoft 365, probably like many of you. And being cloud-based software, we would just get updates periodically. This is my Outlook. And one day I jumped in and there was a new button that said Insights. Tap Insights and this panel here to the right appeared. As I studied the panel, it was pretty clear to me that what Insights was doing for me to assist me is that it was reading my email, outgoing and incoming, and looking for when language was used that implied some future task. I asked, for example, what are my best resources in communicating with Kelly? And by prompting me here maybe a week later, I can say, oh yeah, that requires follow-up, and it will continue to remind me. Or I could say, no, I took care of that. I called Kelly. You wouldn't know, but I called Kelly and it's all taken care of. Or I could just close out the task altogether if there was a misread. Also, as I make these interactions with Insights, it's learning about how I communicate with my colleagues. At the end of the day, this is a great assistance to me or anybody who has a large inbox. Things get pushed below the fold. We know it's easy to forget, and this helps me be more effective. This next example has some automation. It's Gmail. And what Google has done, and by the way, Word has done the same thing very recently, is they've begun suggesting how one might complete a sentence. You see the light gray text appears? That's artificial intelligence. It has learned based on your previous communications and those of others how you might finish that sentence. If you like what it says, you just hit the tab key and you've saved yourself those keystrokes. Maybe you've helped organize a more succinct email. All my spelling errors get removed, and that makes it also a nice advantage brought to us by artificial intelligence. Around the same time, I was fortunate enough to be invited to participate in some training at Microsoft's headquarters. This is my colleague playing with HoloLens, an amazing experience to reach out and touch and interact with things that only you can see in a full stereo experience. Here on the left, you can see our instructor, and his difficult task was to begin to bring us up to speed on the implications of machine learning and artificial intelligence. And for me, that meant, what could we do to make that apply to environmental health and environmental health data managers? Back in 2019, we did a fun presentation at the AEC. We talked about how you could use voice. We actually built a little project where you could say, Alexa, ask the health department what's going on at Lucy's barbecue. And then it would read back the most recent inspection results. Pretty cool, kind of fun. In 2020, unfortunately, we didn't meet, but in 2021, this session, we will ask, can we use machine learning and artificial intelligence to affect more meaningful interventions? And interventions is where I choose to focus today. So the outline of our time together is very simple. We'll talk about why this presentation, how it came together. I'll walk you through an experiment, and then we'll have a few minutes for wrap up and review. I want to be clear from the onset. This presentation is not a sales pitch. We don't have a product to sell, but I want to demonstrate how these commercially and consumer available products, essentially cloud computing, can be brought to bear. My hope is that it raises the bar. I mean, there might be a day in the future where you hear through the grapevine, oh, our IT department just finished its partnership agreement with Google or Microsoft, and they're looking for a good project, one where there's a lot of data. Environmental health always has a lot of data. I would hope you would be able to step forward, raise your hand and say, you know what, environmental health would be a great place to kick that off, and then work with those teams in order to affect a good project. So I'm going to try my darndest to give a baseline understanding of machine language, understand that machine learning, understand this is going to be at a 30,000 foot level. For this audience, it starts maybe by thinking of examples. The first and best example is Google Maps or Waze or even Apple Maps. To me, it's a modern miracle. They consider historical traffic. They consider real-time traffic. They look at weather. They look at closures. They look at routing that's going on through other arteries in order to give you the very best recommended path forward. It's really amazing. Things like Facebook, Google, Apple, even others are now identifying and classifying faces. Several years ago, Google Photos, what I use for my family photos, started grouping people. I didn't have to ask. I just had to answer one question. Here's a face. Who does it belong to? I said, well, that belongs to me. And they go, oh, great. Here are all the photos of you. Oh, that belongs to my son. Awesome. Here are all the photos of your son. And it's a very convenient way to keep your photos organized. And as you know, the technology can go from there. But let's talk about convenience for us. Here's another example. I just downloaded on my phone a really cool app. You might want to download it. It's called Seeing, like looking with your eyeballs, Seeing AI. And it's a camera app where you point your camera at some part of your landscape and it speaks, says, oh, that's a printer. Oh, that's a cup of coffee. Oh, that looks like an office with a closet. Awesome assistance for folks maybe who don't see so well, and a great demonstration of how artificial intelligence and machine learning can assist other folks. Play with that. It's a lot of fun. Voice recognition, medical imaging, in particular scanning for cancers in mammograms and other types of detecting projects, just absolutely amazing. And we know it can go negative too. The news like to amplify the impact of deep fakes and other types of things. We don't get to control what technology is coming to bear, but it is our responsibility to be aware of it and to use it where it makes sense. So we can sum it up this way. If we just use the phrase artificial intelligence, we're talking about the tech that makes machines seem more intelligent than they really are. The ability to do things that historically they haven't been able to do or would require just a ton of programming. And you might hear other similar phrasing, but it's all part of the same family tree: deep learning, natural language processing, the others that are listed here. Just know that those all wrap up in the higher order definition of artificial intelligence. So with that as a baseline, let's think about an experiment we could do. An experiment that has low stakes or low cost of entry, might be kind of fun for the data nerds out there, and is certainly within our reach. And that began with me thinking about how I might organize it. This is how my brain works. So I'll sit down and I'll spec out on the back of a napkin what this project might look like. It avoids me from going too many other directions. I agreed with myself. I would select one of the commercially available services. I would assess what data is available to me and to health departments. I would figure out a problem that we could attack with that data. Then I would run experiments. I would analyze the results, tune, rerun if we had to, and then we could decide whether it was worthy of a proof of concept. So let's begin. Number one, what commercially available system should I use? Well, for me, it was a no-brainer. We're an Excel is the partner to Microsoft, and also I've been through their training. And it turns out they have a free tier. It costs me nothing, zero. Just the cost of putting in my email address and a password got me access. And I'm sure Google and Amazon have similar tiers. They're equally adept, but I chose Microsoft Azure. Then I considered what data I have access to. Well, in my role as assisting with data management for 130 or so health departments, I have access to a lot of data, all publicly available. And this happened to be a list of inspections. Turns out, for this very large health department, I had almost 1 million inspections in our history going back 10 years. When I brought that into Excel and I turned it into a quick pivot, I could see that the number of food inspections completed per year relatively flat, except for the last 2 years. And then my chosen focus, for right or wrong, was I chose to focus on hand washing violations. And the frequency of hand washing violations we can see here was marching pretty predictably upward. And hand washing being, a foodborne illness risk factor seemed like a good case. So we're going to work on hand washing and hand washing violations and potentially interventions around hand washing. So let's think about what the model of the project would be. In other words, what might we ask this power that we're describing to accomplish for us? I said, based on historical inspections and information we know about the facility and the permit, can we predict a hand washing violation? Okay, might be a bad premise, but that's the one we're going to use today. Then I had to contemplate what type of problem is it? And it turns out this is a classification problem. This will be important later on when we set up the model. One of the questions they must have answered is what type of problem is it? And there are other types of problems. There are regressions, where you're predicting a value kind of along a straight line, like the price of a used car. And then there are time series problems, where you predict a state at some future date. Those are perfectly legit, might also apply to environmental health, but ours today, classification project. I also learned the word feature. A feature is an attribute that will feed into the trainer, or we might call it just a field on a screen. Things like inspection type, who is the inspector, number of complaints at that facility, what is their type of ownership. There are literally hundreds, maybe thousands, and they're going to differ health department by health department based on the data system you use and how you choose to populate it. We had a very specific data set here, which I extracted from that large health department that I mentioned, and I had some compelling features, I thought. So here are a couple of them. Activity date, the date the inspection was occurring. Could that have an impact on whether or not we saw a hand washing violation? Well, maybe. Maybe if there were interventions along that timeline, maybe if there were standardization trainings along that timeline, don't know, but it's there. Also the type of service, whether it was a true routine inspection or a follow-up or complaint investigation, what year it took place, inspection time, I think is critical. And it's just so happens that this health department feels the same way. They record the start time for every food inspection. More to the right, we have other attributes of interest, kind of what fee they slot into, or you might say what program element or what they're permitted for, their inspection district, the number of facilities, the number of permits. I even took a shot for the wall and said to myself, I wonder if they still owe us money, if that somehow predicted how they keep the front of the house. In other words, if they're not taking care of their business on the financial side, maybe they're not taking care of their business on the food safety side. I don't know. We have to put them all into the model in order to find out. So at the end of the day, I had to think carefully and after a few iterations about what to include. In this pass that we'll discuss today, I included the profile information on the facility, its type of ownership, how many permits, how long it's been in business. I thought those would be good predictors. I also decided to count complaints, even if they weren't food complaints, complaints against the facility, again, as an input. The inspector and the district also factor in. Although when it comes to district and inspector, there is perhaps some awareness that we should inject into the conversation that if you're talking about district, you might be talking about zip codes. When you talk about zip codes, you're talking about neighborhoods. And when you talk about neighborhoods, you might be talking about a more populated set of folks that is predictable that might not really legitimately be tied to hand washing. So we want to be careful about that. But nonetheless, we're declaring in advance that is our goal. And then I threw away the notion of inspection type. Well, it turns out inspection type is too closely correlated. You see, routine inspections are where you're going to find your hand washing violations more often. And so it became too much of an impact in the model. So I threw it out. And we're only looking at routine inspections to begin with. The date, the day of the week, the zip code for the reasons I described before. And some folks even said, well, bring in the weather. I couldn't fathom how weather could possibly have an impact, so I left that out. But you get to choose. You get to choose at the end of the day. And the whole flow is going to look something like this. We choose our features here on the left. We put it into some amazing computing power that trains the model and assesses the model. In other words, determines whether these features can do what we're asking it to do. And then, if we like it, maybe we use that model to predict the likelihood of a hand washing violation. And why would that matter? Well, it matters because you could tune and focus your interventions to those facilities that fall into that classification. In other words, we can spend our time and effort offering up interventions to those facilities that are most likely to have this particular problem. Make sense? Good. I also want to take a moment and just give a pitch for all the tutorials and demos that are out there on the web. By picking one of the big three, I was immediately lucky to have a million different people trying to do a million different projects. And a lot of those projects, if you think about them, are pretty close to our project. Maybe somebody is predicting, will a person use Facebook based on their age, their sex, their demographic information? Well, that's a classification problem, same as ours. We're trying to predict a hand washing violation. They're trying to predict another human activity. So that type of tutorial was immediately and very relevant to our project. Take advantage of the tutorials. And by the time I got myself into the artificial intelligence machine learning part of Azure AI, the screen looked kind of like this. Now, what I thought to mention here is that it turns out, I learned, there are 3 ways you can start this process. One is as a programmer. So if you know a programming language like Python or Java, God bless you. That's one way to do it. There is also a drag and drop designer That's more my level of entry. And so like Visio, you can drag the component parts onto a canvas, move them around, connect them. You have your control that way. And the third, and the option that I'll talk to you about most today, is about the automated method. The automated method removes from the formula a lot of expertise that I don't yet have, you might not yet have, but we can still get our benefit. For today, let's start with the designer. Let me show you the designer, because what we see in the designer is indicative of what the automated method will do for us anyway. And so it's a good visual cue. This model actually wasn't ultimately very successful, but let's walk through it nonetheless. Each part that you see here came from a palette of available things, and there are hundreds. I used a tutorial to give me a sense of what to do first. And so for my tutorial, I brought in my inspections, same inspections you saw in Excel a moment ago. I selected what columns were relevant to the discussion. We talked about that too. We also get an opportunity to clean up some missing data, and there was some bad data in my data set. What this did is it either threw away bad rows or it applied some defaults. Lots of choices in here. Basically, I just threw away what was bad because we had so many rows to begin with. Here's where I had an aha moment. I'll share it with you. A common practice, maybe a required practice in machine learning, is splitting your data. So I mentioned I had almost 1 million rows. What this step does is it says, okay, I'll take 80% of those rows selected randomly, and I will feed them into this step that trains the model. What do I do with the other 20%? I keep them in reserve, kind of unfettered, in order to score the model later. So this 80% train it, this last 20% are used to test it, as if those were new transactions, new to the model. And then by breaking it that way and coming to a complete scoring model, we can determine whether it's going to be a good model for us. Here's where I got hung up. See this multi-class boosted decision tree? This is a compulsory part of the layout, and it is to instruct the machine what algorithm to use. I've learned through this journey there are 40, probably 100 different ways to approach this problem mathematically. I'm not qualified to pick which one. A data scientist might know, oh, well, this is a perfect project for a multi-class boosted decision tree. I don't even know what that is. I'd have to Google it to find out. And I certainly couldn't pick from 40. So picking the right algorithm was the tough part of doing it this way. Good news is there's a better way that I'll show you in a moment. Nonetheless, the model got trained, and we took the results of that, and we took the 20% we'd reserved, and we ran it through the model to see what the score was, and then we evaluated whether it was successful. This ultimately, using this algorithm, did not score very well. So we're going to throw it out, and we're going to move quickly to the next and better approach. And I know probably the other top 3 providers have the same sort of notion, but over in the Azure world, Microsoft, they say, well, we've got 40 or so formulas here. Why don't we just run all of them? And each one will result in a score. And then we'll pick from the scored models, the one that fits best for your problem, for your data, for your ask. And in this very simple diagram, formula purple here scored the best, and then formula purple then is the one that was used. Might that be the one that I picked over in the drag and drop? Probably not, but it could have been. So the automated approach, very simple. It's a wizard. We all know wizards. And I'll show you this in real life in a second. But this is the screenshot where we select our data set, or we can upload a new data set. Then this is the shot where I can see that same data that I saw in Excel, but I can see it now in the dashboard. Step number 2 of the wizard, configure. I had to answer 3 kind of tough questions. So one was give it a name. Predicting handwash violations was my choice. I had to pick a column. If you tap this little lowercase I, it will tell you more about this. But the target column says, okay, you're giving me 100,000 rows. Which row is the row that you're trying to build your model around? And we decided we're building our model around whether there will be or has been a hand washing violation for that set of circumstances. And then finally, the most nerdy of nerdy questions is I had to answer how much computing power I wanted to dedicate to this problem, because out here in the cloud, they could spin up 100 machines all focusing on this one problem, finish it like that. In my case, my needs were pretty modest. So I picked, according to the demos that I saw, a pretty straightforward, simple machine, kind of like the machine you might even have on your desktop, nothing too crazy. So those are my answers: a name, a target column, and how much computing power I wanted to apply. Remember earlier I described classification, regression, and time series as the three common problems? Here is where that becomes important. I had to choose, hey, yeah, this is a classification problem. It actually is a yes/no problem, right? Are they going to have a violation related to hand washing, or are they not? Regression and time series don't apply in this case, but they're there for us. And then once I finished the wizard, it kind of gave me the status report. It says, okay, it's up and running. It was created on Friday. These are all the doodads of it. And what I learned from watching the demos is that if I switch over to the models tab, then one by one, as it finished those 40 or so models that it has access to, it plops them down here and by default sorts them according to their efficiency. So what appears at the very top is the model that seems to fit best for your problem and for your data set. And interestingly, remember, we're looking at 1,000 rows. This is nothing to sneeze at. This voting ensemble, which I wouldn't know was the right one, but it figured out as the right one, ended up being the most efficient. And the good news is it only took just under 2 minutes to run. That's kind of cool. Some of the other ones took longer and it scrolls down 2 pages, but that told me something kind of cool, that if I continue to use this algorithm, it doesn't take me very long to look at even 1 million records. Okay, now we got to put on our nerd glasses because it gets a little crazy here, but let's keep it simple if we can. We get a dashboard that shows all these different metrics for the project, and they all kind of combine to tell us one thing. Is this a model that we should work with? Does it have the reliability? Does it have the behavior, the attributes that we want? I've only selected 6 or so, but there's just a ton of them here that you could turn on. So before we make any attempt to try to unpack what's there, let's just talk about accuracy for a moment. Accuracy for an average Joe like me might be where I go. I might say, well, how accurate is the model? But I learned from our training that your model could be 99% accurate, but still not worth anything. And here's an example. Think about a model that intends to predict coronavirus infection. And it just so is the case that 95% of your subjects coming in for tests don't have the virus. So the model could guess no infection and be right 95% of the time. We might walk out of the lab going, hey, we have a model that's 95% effective in predicting coronavirus infection, but it's not useful to us. It's not useful to us at all if the efficacy is just equal to the population. Just so happens that most of that time of the population aren't infected. Thank goodness there's a better assessment. That assessment is called recall and precision. And they work hand in glove, almost like the yin and yang of assessing your model. Precision is, of those that were predicted to be true, hand washing violation, how many actually are? So it was predicted true versus true in real life. So if you just look at that part, we could say, well, we predicted 5 and 4 turned out to be in violation. That's an 80% precision. You might go, okay, 80% is pretty good. Now, the complement to that is called recall. Recall says, asks the question in a really different way. Of the actual violations that are out there in the wild, how many did we predict? You see, it's not the same question. It's a related question asked in a different way. So if there were 20 violations out there in the world and we only predicted 4, that's 20% recall, and that's not very good. That's not a very great measure. There's a graph called a confusion matrix that shows how those two things interrelate. But before I show that, this is kind of how it's broken down in most tutorials. True positives in a field of false negatives, false positives in a field of true negatives. And here's that confusion matrix. This is the way it appeared in my dashboard, impossible to read, too small. So I brought forth the numbers here so we can read them. So let's focus on the 2 quadrants that have green boxes. So in our specific model with our million records, probably 800,000 of which were used to train the model, 200,000 of which were used to validate the model, we predicted no violation and found no violation 88% of the time. I like that. That's pretty good. And then over here, we predicted a hand washing violation, and then it just turned out that there was a hand washing violation also around 88% of the time, almost 89% of the time. These other two yellow boxes indicate our failures. And this is represented in another way here, where this graph shows the relationship between precision and recall. A perfect model, the line would go straight along this axis and then straight down this axis. You kind of see that here as the ideal. It's a dash dot dash in purple. These curves represent our averages. And so what's left here in this space above the curve, those are our failures. Those are cases where the model didn't do what we expected. And this space here under the curve are our wins, if you will. There's another way to look at this data called a calibration curve, also available in that same dashboard, which shows the relative frequency of what was observed on the y-axis versus the predicted probability of the frequency on the x-axis here. And in a perfect world, each of these sample points would line up perfectly along the line. And you can see that in our data, we're pretty close, but not perfect. So not perfect. Not perfect, predicting a human behavior, probably par for the course. But let's talk about what it means if we don't like the results. If that's not good enough, the graph here on the left shows a near perfect model. The graph on the right shows our model. It's not that close to perfect. So we go back into our caves and we think about it this way. First consideration, what is the risk and impact of a false positive? In our case, what if we said, we predict a facility is high risk and it turns out they're actually fine? Or we predict a facility will have hand washing violations and it turns out that they don't, they almost never do. Well, that's not tragic. It just means that maybe we applied interventions that weren't necessary, maybe a little bit of a waste of resources. The next bullet is, let's look at the risk and impact of a false negative. So what if we predicted a facility was low risk and it turned out they really weren't minding the shop? What if we predicted no hand washing violations and yet it turns out that hand washing was not part of their culture at all? Well, that impact is more impactful. That impact is more significant perhaps to our conversation, because it means that the public and the consumers are at risk at that particular facility. No matter what you think about this way, it's time to rethink, modify, and do it again. You go back to the early features that we chose to add. Well, I chose to exclude inspection type. Maybe inspection type needs to be in there, or maybe district needs to be out of there. We can do this as many times as needed, and we can get closer and closer and closer to our target until we're as close as we think we can get. One last comment here, important for all discussions of this type, is to consider biases and your ethics in your model. Going back to including zip code or inspector district as a feature, then you may be teaching the model to be overly or inappropriately focused on a particular population, not even intending to, but that's just the way it factors out. So be smart about that and avoid that if you can, and go out of your way to talk about how it was avoided in your particular project. Now, if we like the model, then there's a one push button that says deploy this to the cloud. The computers go beep, bop, beep, and you get a URL. That URL, it's kind of going to be full of numbers and letters, gobbledygook, is not for you. That URL is for you to hand off to a software developer. Maybe it's your vendor, maybe it's your IT department, maybe it's a community advocate who has the technical chops to write an application around it. So writing an application around it can be from A to Z, and I'm not going to say today what it is, but it basically says with these features available to it, we can at any time ask the model, should we expect a hand washing violation? And the model will answer back a yes or a no. That's a classification based on what we've trained it to do. And then your software developer can go and do something with that. And in our premise, we said, we're going to focus our interventions around those facilities that are most likely to violate, so that our intervention efforts are highly targeted. Great, go through all your facilities, feed in all the data, get back a yes or a no, and then go and focus on the ones that are yes. You can also use it for training inspectors. We already talked about using it as interventions. So I want to just go through the experiment one time so you can see it up on the screen. This is my machine learning screen, and I'll make it a little bit bigger for everybody. And these are the three methods that I described. And we're going to use the automated machine language method. These are the projects that are going on. I have one running from earlier today, but I'm just going to ask for a new project. And here's that wizard. I can upload the data set from a local file, which is what I did originally, or I can use the data set that I previously uploaded. That's easy enough. And here are those three tough questions, but I already gave you a hint as to the answers for each three. So let's answer them together today. I have to give the experiment a name, and if I'm iterating, I should use that existing experiment. If I'm creating a whole new experiment, I should give it a new name. So this experiment is called presentation example. Remember, we said of all these attributes that are available to me, what's the one that I'm trying to predict? And it's whether or not there is a hand washing violation. And by the way, I distilled the hand washing violation flag into a 1 for yes and a 0 for no. It's just so easy for computers to understand that, and we understand it too as humans. So that's why it's an integer or a number. And then lastly, I have to choose what kind of computer power I'm going to put to it. And if you choose create a new, then it opens up kind of a pretty easy wizard where it just asks you some questions. And what I like about this wizard is it just has a default. And you can see it's going to cost me 37 cents an hour to use this machine. That's the cost of it if we finally get beyond our free tier. So these all look good to me. So when I click next, I can say it's a classification problem, and that green bubble jumps up here. These others do not apply. Within classification, I can go in and I can specifically say, oh, don't bother looking at serial number, and don't bother looking at inspection type, and don't bother looking at facility ID or facility name. Those won't be predictive. So by turning those off, that has the effect of pulling them out of the system's thinking. And so that I can get to that level of granularity. And then when I hit finish, it says, okay. And somewhere out in the cloud, somewhere in Redmond, someplace maybe out in the ocean, I don't know, machines are spinning up. A compute is prepared for my use. That data is being transferred to it. And as we sit here, the status will change from not started to queued to building your machine to running. And then one by one, it will run the models that are earmarked for this project. As they run and finish, they appear here according to their efficiency. So not too hard. We could definitely do it together. I want to ask the question, what would make this more meaningful? So environmental health has so many opportunities to take advantage of its data, and we don't do it nearly enough. I feel like we keep our data merely for public records requests or for defending our fees, and we're not doing all we should. We could have chatbots that answer questions for inspectors and operators and the public alike. We could predict overall facility risk and use it to define the frequency of our inspections. I know FDA already has a model for that, but maybe we go deeper with our own data to back it up. We already talked about pre-authored inspector comments. I have a column in the Journal of Environmental Health that will come out in September on this topic. I'm excited about that. Routing, looking at photos. Can an inspector take a photo of a sink and then have the system automatically align that photo to the checklist item that would have to do with the prep areas? Of course, we could do stuff like that. And it doesn't just apply to food. Food is easy because we've all spent our time in retail food, but pools have kind of a similar need. There's a lot of risk associated with operating a pool. Just check to the current headlines, and those could benefit from these technology as well. So in wrap up, we learned that tutorials are going to be a great place to start, and there are free services out there just to play with. We also agree that our first pass will almost always be wrong. That's an iterative process, and that's part of the fun of it as far as I'm concerned. That's part of the learning. We also learned that the models created for one region aren't going to apply to another, especially if you're in different data systems, you're under different food code, you have different operations. Just know that that's going to be highly regional and maybe even local to your health department or your health district. And we can always bring in more expertise from our IT department, from NEHA, from a vendor, someone who could get excited to work with you. For my part, I'm very excited about the prospects of what I've learned in this project. And I'll be turning it over to the larger group and giving them an invitation to turn it into something that's more of a proof of concept or a demonstration project, which, if it passes that test, will be part of our annual user conference later this fall. Thank you very much for spending your time with me today. I enjoyed it greatly, and you are welcome to reach out to me or give me a call at any time if you want to chat about this or anything else related to data management. Thank you. Have a great day.